In this video, we'll be using what we learned about quadratic functions to help us solve some practical problems. Specifically, we'll be looking at maximizing revenue from selling a certain product. In economics, revenue is the amount of money received from selling an item. So being able to maximize your revenue will be important, especially if you want to start your own business or if you want to sell a certain product. In general, revenue is very easy to compute. For a certain item that you're selling, you can calculate it by taking the quantity sold and multiplying it by the price per item. For example, if you're selling lemonade and you sold 50 cups for $2 per cup, then you can calculate the revenue by multiplying 50 by 2 to get $100 in total. Now, when we're doing math, we typically like to use variables to represent different quantities. So let's assign some variables for our current situation. Let R be our variable for revenue, Q be our variable for the quantity sold, and lastly, P for the price we are selling our product for. With these variables, our revenue equation then becomes R equals Q times P. Now, our two quantities Q and P are usually related to each other in some way. Specifically, in economics, there's a principle called the law of demand. The law of demand tells us that the two quantities Q and P are inversely related to each other, meaning as one increases, the other decreases. Going back to our example with selling lemonade, if we increase the price per cup of lemonade, fewer people are going to want to buy it, so my quantity sold would go down. On the other hand, if we decrease the price per cup, it becomes more affordable, so more people will want to buy it and our quantity sold goes up. In order to maximize our revenue, we'll need to know exactly how these two quantities are related. The equation describing how these quantities are related is called the demand equation. Companies that sell products usually have market research teams that figure out how much customers are willing to pay for their products. They take that information to determine the demand equation. What we'll do next is look at some examples of maximizing revenue when we are given this demand equation. In this example, we're selling a product. Let P be the variable for the price of the product, and let Q be the variable for the quantity that we're going to sell. Then we find out that the demand equation is given by Q equals negative 10P plus 1500. In part A of this example, we just want to express the revenue as a function of P, meaning we want to write our revenue equals some expression that involves the variable P. From what we talked about earlier, we learned that revenue is equal to quantity sold times the price. So we have the relationship that R is equal to Q times P. But at the moment here, our revenue is dependent on two different variables, Q and P. What we're interested in, though, is writing R just in terms of P. So how do we get rid of the Q? Well, we're going to use our demand equation. We can make a substitution using this demand equation. I know that Q is equal to negative 10P plus 1500, so I can replace the Q in this equation by this expression. Replacing that Q, we get the equation R is equal to negative 10P plus 1500 instead of Q, and then times P. And now we can simplify this expression by distributing that P to each of the terms inside the parentheses. So we end up with R equals negative 10P squared plus 1500P. Now we've rewritten our revenue just in terms of P, and this is our answer to part A. What we notice here is that our revenue is equal to a quadratic because of that P squared on the right-hand side. Let's take a moment to look at the graph of this equation. Now, the equations we've looked at previously were typically of the form y equals something involving x's. But instead, our equation here has r equals something involving p's. So it's like r is taking the place of y, and the p's are taking the place of x's. So if we were to graph this equation, instead of graphing this on the xy plane, our x-axis will be describing our p variable, which is telling me about the price, and our y-axis is telling me about the r variable, which is our revenue. Since our r is equal to a quadratic, we know that the shape of the graph is a parabola. And specifically, because of this -10 in front of the p squared, we know that our parabola is going to be vertically reflected, which means that we have a concave down parabola. So let's sketch a graph of a concave down parabola, and you might get a shape that looks something like this. Now, for any point A, comma B that we have on this graph, we know that the first coordinate here, the A, tells me about the price, and then the second coordinate, B, tells me about the revenue. And since this is a point on the graph of this equation, it's saying that when I set my price to A, we're going to get the revenue B. So one point that I know for sure is on my graph is the origin, 0, 0. Because if I set the price of my product to be $0, no matter how many I sell or give away, I'm going to make $0 in revenue. Now let's take a look at what part B of our problem is asking us for. It's asking what price maximizes the revenue and what is the maximum revenue. If we want to find the maximum revenue, we want to look at our graph and determine where our highest point is, because our vertical axis is telling you about the revenue. So the highest point will be the point with the largest revenue. And the highest point of our graph happens to be the vertex of our parabola. So if we can find the vertex of this parabola, we will not only know what price will maximize the revenue, but also what the maximum revenue is. If we want to determine the vertex of the parabola, one thing we can do is rewrite our quadratic function in standard form. In part B here, we'll try to write our revenue in standard form. Our first step is to factor the number in front of the p squared. So we have r equals -10 times. If I have -10p squared and I divide by -10, we're left with just p squared. And then if I have 1500p and I divide by -10, we end up with -150p. Our next step is to complete the square. So let's rewrite our equation. We have r equals -10 times p squared minus 150p, and then we'll leave ourselves a little bit of space before we close the parentheses. Now remember, to complete the square, you want to look at this term here, the -150p. Specifically, take the -150, divide that by 2, and square the result. So -150 divided by 2 gives us -75, and then -75 squared, this gives us 5,625. Now, if we just add 5,625, we'll be changing our equation, and we don't want to do that. So to balance things out, we'll also subtract by 5,625. But now what we can do is we can factor the p squared minus 150p plus 5625 as a square. We end up with r equals -10 times p minus 75 squared, and then at the end we still have that minus 5625. We know this blue part factors as p minus 75 squared because when we complete the square, the number that's with your variable is always half of this middle number. Now there's just one last step to write our quadratic in standard form. We just have to distribute the -10 to each term inside the parentheses. So this gives us r equals -10 times p minus 75 squared, and then plus 56,250. Now that we have our quadratic in standard form, we can easily identify the vertex. To find the first coordinate of the vertex, we flip the number that's with our variable inside the square. So our first coordinate is positive 75, and then our second coordinate is the number that's at the end. That's the 56,250. And remember, this is the highest point that's on our graph. And specifically, the first coordinate here tells me about the price, and the second coordinate tells me about the revenue. And now to answer part B of our problem here, we want to set the price of our product to be $75 to give us the maximum revenue. And when we set our price to be that amount, our revenue is going to be $56,250. And now all that's left is part C of our problem. In part C, we want to determine how many units of our product will be sold at this price. So essentially, we want to determine our Q. Now, from the beginning, we have this relationship that revenue is equal to quantity sold times the price. So if I want to figure out the quantity sold, well, we can just take the equation R equals Q times P and divide both sides by P. This leaves us with R divided by P is equal to Q. So to find the quantity sold, all we have to do is take the revenue, which is 56,250, and divide it by the price of our product, which is $75. So our quantity sold is 56,250 divided by 75, and we end up with 750 units of our product sold. The main takeaway here is that if we know the demand equation, we can turn our revenue equation into a quadratic function. And once we have a quadratic function, we can determine its vertex to figure out the maximum. Let's work through another example like this. In this problem, we're still selling a product. We have the variables P for the price of the product, Q for the quantity sold. This time, the demand equation is given by Q equals negative 3P plus 480. Again, in part A, we want to write the revenue as a function of the price. We can always begin with saying that revenue is equal to the quantity sold times the price, R equals Q times P. But at the moment, our revenue is dependent on two different variables, Q and P. We want to get it down so that it just depends on P. In order to do that, we're going to make a substitution using our demand equation. We're going to replace our Q here with negative 3P plus 480. So our revenue function looks like R equals negative 3P plus 480 and then times P. And then we can simplify this by distributing our P to each of these terms here. We get that the revenue is equal to negative 3P squared plus 480P. And again, if we were to graph this equation, we would get something that looks like this. Instead of having an X and Y axis, our graph here has a P and R axis because in our equation, R is taking the place of the Y and P's here take the place of X's. The shape of the graph of the equation is an upside down parabola because we're working with a quadratic and specifically the coefficient in front of the P squared is negative 3, which means there is a vertical reflection. In part B of our example, we want to determine the price that maximizes the revenue and figure out what the maximum revenue is. To determine these things, we need to find the vertex of this parabola. Since this is the highest point in our graph, it is the point that has the highest revenue. Now, if we want to determine the vertex from our equation, we need to write it in standard form. So our first step in writing our revenue in standard form is by factoring the number in front of the P squared. So factor out a negative 3, and to figure out what's remaining, you take each term and divide by negative 3. So negative 3P squared divided by negative 3 leaves us with just P squared. 480P divided by negative 3 leaves us with negative 160P. Our next step is to complete the square. So rewrite this as R equals negative 3 times P squared minus 160P, but leave yourself a little bit of space before you close the parentheses. Now to complete the square, we want to look at the negative 160 here. We want to divide that by 2 and square the result. So negative 160 divided by 2 gives us negative 80, and negative 80 squared gives us positive 6,400. But I can't just add 6,400 because that changes our equation.
To balance things out, we also need to subtract by 6,400 so we don't change anything. But now what we can do is we can factor the p squared minus 160p plus 6,400. This gives us r equals -3 times p minus 80 squared, and then we still have the minus 6,400 at the end. We know that p squared minus 160p plus 6,400 factors as p minus 80 squared because in the completing the square process, the way it factors is always your variable with half of the middle number. That's why we have a minus 80 here. Now, there's just one last step to write our quadratic in standard form. We just need to distribute the -3 to each term inside the parentheses. This gives me r equals -3 times p minus 80 squared. And then -3 times -6,400 gives us positive 19,200. Now that we have our quadratic in standard form, we can easily identify the vertex. For the first coordinate of the vertex, you want to look within the square, look at the number that's with your variable, and flip the sign. We have a -80 with our p, so the first coordinate of our vertex is positive 80. And then the second coordinate of the vertex is the number at the end. So that's going to be 19,200. Remember that for any point that's on our graph, the first coordinate tells me about the price, and the second coordinate tells me about the revenue. So to answer part B of our problem, the price that we want to set for our product is $80. And at that price, the maximum revenue that we're going to receive is $19,200. In part C, what we want to do is figure out how many units of our product will be sold at this price. So remember that we have this relationship that revenue is equal to quantity sold times the price. So if you want to find the quantity sold, you take this equation and you divide both sides by the price. You get the relationship that the quantity sold is equal to revenue divided by the price. So using the revenue and price that we obtained from part B, we have that the quantity sold is equal to 19,200 divided by 80, and we get 240 units of our product sold. So in this video, we learned how to apply what we know about quadratic functions to help us maximize revenue from selling a product. We saw that if we have the demand equation, we can turn the revenue into a quadratic function, which we can then maximize by finding the vertex.